With that, I'm going to introduce Dr. Savage. Dr. Sam Savage is an adjunct professor in civil and environmental engineering at Stanford University and executive director of probability management, a nonprofit devoted to making uncertainty actionable. Dr. Savage is also the author of The Flaw of Averages, Why We Underestimate Risk in the Face of Uncertainty, and is the inventor of the Stochastic Information Packet, SIP, a standardized data array for conveying uncertainty. And so he's very qualified to talk to us today about how to manage risk in big projects. And he'll also be teaching with us in the winter. You saw some of those slides at the beginning, at CEE 242R, a course on project risk analysis. This is a graduate seminar, but we are accepting people from outside Stanford. So if you are an online learner who might be interested in joining that class, you can enroll. Just go to SCPD's website. Okay, with that, I'm going to turn over the presentation to Sam, and you'll take it away.
All right. Thanks, Pat. I know that we have people with probably a very broad background in their education, and I like to start by leveling the playing field by starting out with something that everybody understands. These are the differential equations of motion of a bicycle. The point of this slide is to show that you do not learn to ride a bicycle through the seat of your intellect, but through the seat of your pants. And I have a name for this. I call it limbic analytics. The limbic system is that part of the brain that connects the reptilian brain to the rest of the stuff between your ears. And computers have allowed us to learn formerly difficult stuff with our limbic systems. It's really very exciting. So I refer to limbic analytics as connecting the seat of the intellect to the seat of the pants. In my book on the flaw of averages, there's a cartoon of this by the cartoonist Jeff Danziger. So here's someone connecting the seat of their intellect to the seat of their pants. And so the philosophy of the course, and by the way, new technology has really enabled this approach in analytics. And I want to start out now with the notion of the flaw of averages. So the flaw of averages explains basically why everything, oops, come on up for here. Why so many projects are behind schedule, beyond budget, and below projection. And we're just going to start out with the behind schedule part. So suppose the project involves creating a new website, and it consists of 10 pages. We've got the shopping cart page and the legal page and the credit card page, whatever. Naturally, we're uncertain about how long each page will take to complete, but they are being created in parallel by 10 separate teams. So this is the best of all possible projects. Team 1 does page 1, team 2 does page 2. When we get all 10 pages done, we can launch the website. But of course, we're uncertain about how long each team will take. So on average, they take 6 weeks, but ooh, you know, that could happen, or that could happen, or that could happen. But on average, they're 6 weeks. So here's where the flaw of averages comes in. The boss comes in and says, hey, when's the website going to be up? And you say, I don't know, boss, because I don't know how long page 1 will take, or page 2, or page 3. And then the boss says, correct me if I'm wrong, give me a number. Now, give me a number is actually the fork in the road to hell, because after you've done that, you really can't do any more analysis if you give them a number. But you say to the boss, I can't give you a number, but I can give you an average. Because on average, each of these is 6 weeks. So on average, this project will be done in 6 weeks. And the boss says, well, if all you can give me is an average, okay, and you've told me 6 weeks, so that's what we're thinking about. Now, like to ask you a question here. You don't have to answer it on a poll because we've already done this poll. Just think for a second. What is the chance that this project will actually be done in 6 weeks? 100%, 50%, 1 in 4, 1 in 10, 1 in 100, 1 in 1,000, 1 in 10,000. I'll let you think for just a bit on that. Last year we did a poll on this, so I know the answers. I know what you think the answers are. Okay, here goes. Most people think, oh, 50-50 chance will be done in 6 weeks. The correct answer is 1 in 1,000. And it's not enough to just understand that, but you've got to be able to explain it to your boss or say a 10-year-old, okay? So let me explain why it's 1 in 1,000. Imagine that each of these 10 pages, the duration of each of the 10 pages is either over 6 weeks or under 6 weeks, determined by a coin toss. Well, the only way that you go live in 6 weeks is if all 10 of these come in at 6 weeks or under, and that's like flipping 10 heads in a row, which is actually 1,000 in, one chance in 1,024. So that's why the answer here is about 1 in 1,000. Now, I think it's important to point out that there have been some technological breakthroughs that have enabled a new discipline that I call probability management. And probability management makes uncertainty actionable by storing it as auditable data. As an example, let's do dice here. I'm going to start out with dice, then we're going to go back to that scheduling example, which is kind of like the granddaddy of all the big flaw of averages problems. So here I've got data representing 10,000 die rolls for each of 3 dice. If you've heard of Monte Carlo simulation, then these data arrays are just the output of a Monte Carlo simulation. But here's the cool thing. There's been a breakthrough in Excel where there's a function called the data table, which has recently become much more powerful. And so by looking at these dice, by the way, see there's trial 1 is a 4, a 6, and a 5. Trial 2 is a 3, a 2, and a 6. Trial 8,700, is it that one? No, that's not it. Let me try 7,005. Well, or this one, I don't know, sorry. One of them in there is 3 ones, and I forget which one, but it's auditable data is the point. 9,765, is that it? There we go. See, I haven't memorized all 10,000 trials. I knew it was one of those. Okay, but that's amazing. So that means that this whole simulation approach is auditable. But watch this. I can say, what happens if I roll that first die 10,000 times? Get out your stopwatch. On your mark, get set, go. Okay, that was 10,000 die rolls. What happens if I add 2 dice together? So I'll add the first die to the second die. And now what I'm doing is I'm doing arithmetic with uncertainty. Now, when you add 2 dice, the smallest number you can get is a 2, the biggest number you can get is a 12. You get those with equal likelihood. See, this histogram we're looking at says, oh yeah, all the dice come up, all the sides come up equally likely. But if I add 2 of them together, whoa, and that was 10,000 Monte Carlo trials in native Excel. Well, then I see there are more 7s than anything else because there are more ways to get a 7. Now, in the discipline of probability management, where we store uncertainties as arrays of data, these things have names, these arrays. I decided to call them Well, I already knew that, the audience out there has got bit and byte, permanently tattooed into your brain somewhere. So I knew I needed SIP and SLURP just to fit into the receptors you already had. SIP stands for Stochastic Information Packet. That's one of these columns. And SLURP is tortured, but it's Stochastic Library Unit with Relationships Preserved. We may or may not get to that during this lecture, but it's very important when you have multiple uncertainties to preserve any interrelationship between them. So now let's go back to the scheduling problem. First thing to say is, gee, how do you define the flaw of averages? Well, the flaw of averages states that plans based on average assumptions are wrong on average. So, for example, oh yeah, most people think this will be done in 6 weeks and 50-50 chance. Right, no, there's one chance in 1,000. That's not close enough even for government work. So here's one example of the flaw of averages. Consider the statistician who drowned in the river that's on average 3 feet deep. Again, this is another cartoon by Jeff Danziger, who's illustrated the book. Here's a more sobering example. Consider a drunk wandering back and forth on a busy highway. His average position is the center line. Well, that means that at his average position, the drunk is alive. Yeah, but on average, he's dead. Not close enough even for government work. Now, this was discovered. This is a mathematical principle known as Jensen's inequality. And just one of the other points here, in the Flaw of Averages book, one of the big problems here in statistics is that most people who had a statistics course have got what I call post-traumatic statistics disorder, or PTSD. And so it's important not to use too much statistical jargon. So in the back of the book, I have a glossary. Well, first of all, I have a term for these words that bring on PTSD. I call them red words. So let me just show you the red word. The green word, green means it's okay. You can say it, the flaw of averages. You can say the flaw of averages. The red word equivalent that you heard in your math course or statistics course is Jensen's inequality. And the formal definition of a red word is something that could not be uttered in a singles bar, for example. But anyway, there is a glossary in the back of the book of these red words and green words. And you don't really need to zoom in there, but when you get there, they're written in Dracula font. This was the publisher's idea. I love it. So I go back now to the drunk in the road. Mathematicians have known about this for over a century as Jensen's inequality. I call it the flaw of averages. This is a public relations issue here. And as a public relations issue, I developed an audio logo for the flaw of averages. So well, here, you recognize this audio logo. You should be able to hear this. That's, of course, a big chip maker. You should recognize their audio logo. Here's the flaw of averages audio logo. So let's go back now to this project model. And I'm going to show you now how we actually can make actionable decisions based on uncertainty. To start out with, we have a SIP library. That is to say, this was not your first rodeo. You've been building web pages for a while. You know how long it takes to build web pages. Yeah, it's uncertain. We can model that uncertainty with a SIP library. So here we have 1,000 possible scenarios. And so when I'm scrolling through, I'm looking through each of 1,000 possibilities. Oh, you wanted 10,000? We could do 10,000. You want 1,000,000? We could do 1,000,000. That would be Excel's limit, but you want to do it in Python or R or something else, you could do 100 million if you needed to. 1,000 is probably enough. So This is a business problem, however. Unfortunately, someone has promised this job in 7 weeks. And if you miss 7 weeks, then there's a $100,000 per week late penalty. Lucky they didn't promise 6 weeks. So let's take a look at this. If I plug in the averages, then I'm done in 6 weeks with no penalty. Yeah, but we know that can't happen, right? Like there's scenario 1, 68,000 in penalty, 7.7. Here's scenario 2. I don't want the output given the average input. I want the average of these over all 1,000 trials. That's what the flaw of averages distinguishes between. And this again is just a native Excel file. You can download this off the probabilitymanagement.org website and share it with 1.2 billion of your closest friends. It's just native Excel. I didn't show you this before, but we're using the data table out here to run 1,000 trials, with every keystroke basically. And so now let's take a look at what the average results are, average over all 1,000 trials. So the outcome of the average inputs is 6 weeks and no penalty, but on average, it's 7.8 weeks and $86,833. The difference between these two is the flaw of averages. Now, how would we use this to make better decisions? Well, the first thing is you go crawling back to the counterparty on your hands and knees and say, oh, please, 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 would you lower our penalty to 50,000? Because notice you're getting nailed here. On average, it's like almost 87,000. So let's lower the penalty to 50,000, right? And they say, oh, we'd be happy to do that, but then we're going to demand that you finish in 6 weeks. Oh, no. Now our penalty is $92,000. Oh my God. So you say, wait a second, how about would you give us 8 weeks to finish? And they say, sure, we're happy to do that if you finish, if you are willing to accept a $150,000 penalty, and you say, sold, that's 23,000 on average. Okay, so really, what's important here is that the discipline of probability management is going to let us determine, number one, the true average of things happening, and number two, the chance of things happening. So let me show you a couple of other examples of the flaw of averages, just so you understand that this is not an isolated phenomenon, but is actually ubiquitous. So I don't know if anyone has ever heard of the potential of, say, sea level rise or just flooding in general. Here's an example where we have a little municipality. They have a creek that floods. There are dikes along the side of the creek. The average flood crest, by the way, is 2.4 meters. And the height of the dikes is 2.5 meters. So given the average flood, there's no damage at all. Here's a little table of damage down here, right? So at 1.82 meters, the nursery school floods, it's $1 million. Then the firehouse at 5 million, then the railroad station at 10 million, the airport at 20 million, finally the hospital up here at 5 meters. So let's remember, it's easy to get a SIP library. The SIP is this array of potential floods, and this is why we have a National Weather Service, to provide these things. Because let's remember a bunch of stuff could happen. Like there are actually 1,000 floods in here. That could happen. Oh yeah, it could, could go way down. Oh, or that could happen. or that could happen, or that could happen. Oops. So what's happening is, on that trial, we had 30 million in damage. But of course, given the average flood, there's no damage. But what if you averaged over all possible floods? Then the damage is going to be $5.5 million. So this is an absolutely ubiquitous problem. Now, the course is going to use my book, and I do not want to induce PTSD in people. So it really turns out there are these 5, I call them mindles, okay? A mindle is for the mind what a handle is for the hand. A handle lets you grasp something like, you know, like a hammer. A mindle lets you grasp one of these slippery concepts. So the mindle for the flaw of averages is the drunk in the road or the statistician in the river. But basically, one section of the book is devoted to the mindles, and it's not even a big section, but they're all 5 mindles. There are only 5 concepts. They're all basically on one page in the book. For those of you who have the book, by the way, it's on page 47. There are 5 things you really have to understand to improve your risk intelligence. Risk intelligence is an important concept. That's what Lindbeck Analytics does, is improve your risk intelligence. You don't have to go off and look at things like the differential equations of motion of a bicycle. You can just know that stuff is wrong. So let me give you one other really interesting example of where this whole probability management approach is being applied. It just means that we are representing uncertainties as arrays of data. It doesn't just work in Excel, it works anywhere. There's this open standard called the SIPMath standard that can be applied in R, in MATLAB, in Python, in Excel. And one of the interesting places we're beginning to apply it now is military readiness, actually. So this is a conceptual model of an air wing on an aircraft carrier. You have so many strike fighters and growlers and these things. And, you know, these planes are not flying all the time. You know, they might be up about 80% of the time, but, you know, they're fixing the flat tires, they're emptying the ashtrays or whatever the heck they do to keep the planes flying. And so you might have a mission requirement. You say, listen, if we have to fly this mission today, I need 30 strike fighters, 3 growlers, 3 of these radar planes, 1 of these, and 12 helicopters. What's my chance of being ready? So let's go back to give me a number. So give me a number. Give me a number is the fork in the road to hell. The course is going to teach you how to deal with that with the boss. And I'm just going to give you the bottom line. When the boss says, give me a number, you say, what do you want it to be? I'll tell you the chances. Very important. So if the boss wants this many aircraft of these types, you say, well, your chance is 61% of carrying that mission off today. If we just have to do it at random, bam, we have to fly this thing, 61% chance. So the boss says, well, gee, what if I back off the strike fighters? And oh, by the way, if we look down at the bottom of this sheet, we're also learning the chance that any particular type of aircraft was holding us up. And we see that the strike fighters, in the event that we can't fly the mission, there's a 43% chance it was the strike fighters, 35% chance it was the helicopters. Well, what if I back off to say, you know, 25 of these, and I back off the helicopters to 10? Whoa. By doing that, we've increased our chance of being able to fly the mission to 82% from 61%. Now, which mission to attempt to fly is above my pay grade. But the person who makes that decision should be informed with chances, not with averages. All right. So let me now show you a bit how we solve these problems from scratch. And oh, I'll tell you what, because this course is actually in project management, here's something I just have to show. This is a template that just came straight out of Excel. If you go to Excel and you open templates, you open new file and you put in a little search and you put in like project planning or something, this template pops up. And we simply modified this to take in SITMath. So SITMath meaning this open standard for using the data table to do simulations. So I'm going to check this little box, click, whoa, suddenly this thing is in simulation mode. And you can do that or that or that or that. By the way, one of the things we do in the class is I have students go out and download these various project planning templates, and then they can add their own probabilistic stuff into it. So this is taking this ready-made template, and yeah, there's a little work to do it, but not that much work to hook it up to the data table. So that's definitely one of my favorite models. All right, so let's now talk about sort of applying this and the stuff we're going to learn in the course for building models. Oh, and before I do that, I realize I can do it after. This is all based on something in Excel called the data table function, which you find here. Data what if analysis data table. Now, the fact is, there's some free tools out at the nonprofit's website where you can, I'm going to demonstrate the tools in a second, and they help you build the data table. So you don't really need to do this from scratch. But let's look at this model. I told you that the flaw of averages explains why so many projects are behind schedule, beyond budget, and below projection. This is the below projection project. And basically, this would be something like a capital investment project. We have to build a factory or something to produce things, or I'm going to make a really simple version where we just have to order stuff for the Christmas season. But the point is, we have an uncertain demand for a product. So here the cost per unit, you got to order 6 months in advance. Cost per unit is 30 bucks. Selling price, 40 bucks. We know that with certainty. We're uncertain about the demand, and again, we have to order 6 months in advance. But everybody agrees the average demand is 100,000 units, so we order 100,000 units. Now, the boss comes in and says, what's profit going to be? And you say, I don't know, boss, because I don't know what demand is going to be. And then the boss says, give me a number. And you say, would you settle for an average profit? The boss says, if it's all you can give me, you say, well, that's easy enough. We plug in 1,000 for our demand, and revenue is 40 times 100,000. We got 4 million, and the cost of goods was 30 times 100,000. That's 3 million. So the profit is 1 million. Yeah, that's the profit of the average. But is that the average profit? So it doesn't take long to find out. What would happen if the demand was 90,000? Well, if the demand is 90,000, you only make $600,000. Sure, but what if the demand was 110,000? See, what I'm doing here is I am experimenting with a model. What if the demand is a little higher? What if it's a little lower? So if the demand was lower, we went down to 600,000. What if it's a little higher? Uh-oh, we're still at $1 million. We're capped at $1 million. You can't make more than $1 million because you only ordered 100,000 of these widgets, whatever they are. So let's go back to 100,000. We see that the profit of 100,000 of the demand, if the demand is 100,000, the profit is $1 million. But if profit goes down, we make less money. If profit goes up, we don't make more money. How could something less than $1 million and something equal to $1 million average out to $1 million? It can't. The average isn't $1 million. That's the best possible case. Now, I'm going to invoke the SIPMath modeler tools. And again, the website is probabilitymanagement.org is the nonprofit where you can grab these. And here's what I'm going to do. In this case, there is a SIP library waiting for me to plug in to this cell. I don't know how to do Monte Carlo simulation to do this. All right? Let me give you an analogy here. I presume that many of you have heard of Monte Carlo simulation because again, it's not my first rodeo, and I know that people who show up for these things, they've heard of Monte Carlo. A technique developed during the Manhattan Project where they developed the atomic bomb. And to use Monte Carlo simulation, you have to know a lot about statistics. So you have to know how to generate all these random numbers that go into your model. And that's why people can't all use Monte Carlo. Well, that's one reason. The other reason was you had to buy expensive Monte Carlo simulation software. Okay, now you don't. Now Monte Carlo will run in native Excel. So we got that problem out of the way. But we still have the problem of, well, I'm not an expert. How would I know how to generate the random numbers? Well, let me ask you something. Do you use light bulbs by any chance? I'll bet you do. Do you know how to generate the electricity that goes into the light bulbs? I bet you don't, unless a few of you are working in a power company right now. So how did we work that out? Well, we had the electrical engineers generate the power in power plants and then distribute it over power lines to the people who needed it. And to do that, we had to invent the 60-cycle AC current standard. Actually, the people who invented it were called Westinghouse and Tesla. So now that we have that standard, we can distribute electricity from the people who generate to the people who need it. We can now distribute probability distributions from the people who know how to generate them to the people who need them. I call this distribution. So what I'm going to do is now use the SIPMath tools, and it now wants, I could generate my own electricity if I knew if I were a statistician, but suppose I'm not. I'm just someone who wants to predict the profit here, and I'm going to go to an external workbook. And so I'm going to browse to a workbook called Demand. This workbook has in it a SIP of demand. Here's that workbook. He just opened it for me. And well, where's the SIP? Oh, it's right there. It's a plus sign. All 1,000 trials of demand. Good, okay. And then it's got some metadata in here. And it's in this open standard format, the SIPMath format, which also could be done in XML or comma-separated values or whatever. So now I'm back at my model. The next thing I do is I put my cursor in that cell and I go to library input. And oh, there's demand. So it now knows I have demand. I click OK. I'm going to overwrite the number. Oh, wow, now I have a little picture of a distribution in that cell. How about that? All it's done is put in an index statement to that other file now. And so I could look at, say, trial 1, trial 2, trial 3. I think trial 9 is kind of a... Oh yeah, trial 9 is pretty nasty, isn't it? Demand was 66,862. Yeah, you lost 325,000 on that trial. Let me go back and set it to the average. So, given the average inputs, we're making $1 million. You might want to know what the real average is, by the way. So I put the cursor in that cell. I click on Define Outputs. I give it the name Profit. Oh, and let me just show you something here before I do that. When I initialized the model, it created a separate sheet where the data table is going to be established. Remember, at every stage, I have a model that can be shared with 1.2 billion people. The tools are like saw and hammer, working on wood. If you build a doghouse out of wood, you don't need a saw and hammer. The dog doesn't need a saw and hammer to use the doghouse. No, it's just, so Excel is the wood out of which we're building stuff. And I just showed you this data table sheet. There's nothing on it yet. But as soon as I say define outputs, and I'm going to give it a name, Profit, I click OK, and 1,000 trials later, oh my goodness, there's a SIP of 1,000 profits. Oh yeah, well, duh, the biggest number you can get is 1 million because you only ordered 100,000 widgets. Okay, now, first question you might ask is, what is the average profit? Well, this data table over here is actually named this range. If I look at that range of outputs, the range is called profits. Here's a range name, if you know what range names are in Excel. So I could simply go to the model and I could say, okay, what's the average profit? And I could type in equals average of profit. And it says, oh, 600,000 roughly. The profit of the average was 1 million. The average profit is 600,000. Not close enough even for folk music. All right. Now, the real question is, what are the chances? Right. So how do you know you're doing probability management? You're able to answer questions of the form, what are the chances of something? For example, the boss might say, well, what's the chance of making 800,000? And how do we do that? Well, let's see, 800,000. I want the chance that I'm greater than that. I go over here. I click on the chance of whatever button. Here's my output. The chance that the thing is greater than 800,000 is 58%. Now, of course, I'm an expert, so I knew that. I could do that in my head, but you probably would have needed to do a simulation to find out the chance that it's greater. By the way, what's the chance that it's greater than 900,000? 54%. Now, I want to get to more of the stuff with the tools. I had a nice question sent in to me that I want to get to, but let's just do one other kind of decision-making exercise here. I hope you didn't tell the boss to expect $1 million, which you would have done if you'd plugged in the average demand and then read off the profit. But you probably did. Too bad. Now let me ask this. Why is it 100,000? Why is it only 1 million? Why are we capped at 1 million? Right? So in other words, if I go up to a higher, let's go to a case where I have, oh well, no, this is good enough. My actual demand is 141,000, but I only have sales of 100,000 because all I can sell is what I ordered. So if the actual is greater than the ordered, I only get to sell the ordered, otherwise the actual. This is an if statement in Excel. It means if. It's not that complicated. So I didn't get to sell those extra ones. So maybe I should have ordered more. Like, what if I ordered 120,000? Would that be better? Let's try. Uh-oh. If you order 120,000, your average profit is below 300,000. That's a disaster. What if I ordered less? Let's say order 80,000. Oh, my profit's more. I went up to 60, almost 680,000. And by the way, this is where limbic analytics comes in. Here, Control Z, Control Y. Control Z, back to ordering 100,000, Control Y, ordering 80,000. When you think limbic analytics, you should think the scene in Jurassic Park where Jeff Goldblum is waving the flashlight in front of the Tyrannosaurus to keep it from eating the Jeep with the kids in it, all right? Motion, you've got to do things interactively to get the boss's attention. Okay, let's see if in the time remaining I can quickly answer what I thought was a very good question here from someone on how to model cash flow and when you might run out of money. So a very common thing in a project is that you have to start off by funding a project with, say, $1 million, and then eventually you'll start bringing in cash. But you don't get it right away. So let's say that our cash out in this project, our cash out is, by the way, we have $1 million in funding, so that's our cap. But we have to put in like 250,000 in the first month and 250,000 the second month. Then we work our way down 100,000, 100,000. By the way, it takes $100,000 just to keep the thing operating. But then the cash starts coming in. No cash first month, no cash second month. But, you know, then you get, that's going to be 50,000, then 100,000, 100,000, 100, and then it starts in month 8, it starts ramping up to 200,000. And if you look at that, here's your cash position over time. Now this model already exists. I should point something out. What would happen if we required like 600,000 here? Well, then you can see we get down very close to zero, but we don't get to zero. What if I needed 700,000 or 800,000? Oh, well, once you get to zero, you stay at zero. When you run out of money, you're dead, okay? So there's the model, basically out of the box, violating the law of averages. So now let me show you how we would basically use the tools to model this. And what I'm going to use here, we'll be learning how to use the tools in the course. So I'm not expecting you, but by the way, there are online tutorials and things. So I hope that you'll download the free tools, but it does take a little training to do this stuff, because now I'm not just using SIP libraries, I'm actually learning electrical engineering, you know, how to model the uncertainty. And one very simple way to model uncertain situations is with something called a triangular distribution. And the triangular distribution is pretty brain dead, let me say, but I'm going to use it to get us started. So my first step here is I have estimates for each of these months. This is for my cash in. I have a minimum, a most likely, and a max. And I'm going to turn those into uncertainties in the model. So now I'm going to initialize the model. I'm going to say, I'm in generate mode. I know what I'm doing. I'm going to generate my own electricity. I click OK. And then I'm going to go to the cash in section. And I'm going to go to generate input, and I'm going to say this is going to be a triangular distribution. And I have the minimum, and I have the most likely, and I have the maximum. Now, it also needs me to put in one auxiliary set of data here to put in some additional random numbers that drive the triangular distribution. But now the cash in column has got uncertainties in it, and I can scroll through them here. Trial 1, trial 2, trial 3, trial 4, trial 5, trial 6. Went bankrupt in month 5, right? And so let me put that one away. Because I got one in the oven all ready to come out here naturally, right? I mean, let me show you what you get to eventually. So here we have a model in which it's pure Excel. So I don't have to use the tools to scroll through the trials. Let me point that out. There's this number on the PM table sheet, which is called PM index. And so I can control it from here. There's trial 1, trial 2, trial 3, trial 4, trial 5. Went bankrupt in month 4. I have here a cell. This column of cells tracks the month in which I went bust. And if I don't go bust at all, it puts 100 in there. And up here, I have the minimum of those. So, oh yeah, I went bust in month 4. If I go back to trial 1, 100 doesn't mean I went bust in trial 100. It means I didn't go bust at all. And so looking for the average of when you went bust isn't even a sensible thing, because you might never go bust, right? The company might last forever. You can't average like infinity in with a bunch of, well, I can ask the chance. What's the chance I go bust in 4 months? 14%. How about 5 months? 6 months? How about 12 months? 13 months? Well, 13 months is the highest. I mean, this means you didn't go bust. But that means there's a 43% chance you will go bust within the first year, which is important. And then you could ask little questions like, well, what if we went for more funding? How about 1.2 million? Well, that didn't help that much. Okay, how about 2 million? Oh, no, wait a minute. Hold on. Let me undo. I was looking at the wrong cell. 43% chance of going bust with 1 million. Okay, 1.1 million. That drops to 6%. Oh, that might be something you'd like to know if you're funding this project, right? 1.2%. 0 chance. So sorry, I messed that up again. But you can see now with undo and redo, look at this chance. We'll do a little limbic analytics. Chance of going bust with $1 million worth of funding, 43%. And then let's see, control Y, 1.1 million, we're down to 6%, 1.2 million, we're at 0. Okay. So there's an example of the kind of stuff that most people aren't even doing. They're not talking about chances. They're plugging in averages, they're getting horrible answers, and that's where they stop. So, and this is where I would like to stop and take a few questions.
Thank you so much. Thank you so much, Sam. So we have only a couple minutes, so I think there's one kind of trying to sort of organize all the questions into one central question. So I love this idea of limbic analytics, and we know even that from studies that most statisticians don't think accurately about statistics outside of when they're doing the actual statistical work. So a couple questions have come in about how do you deal, how have you seen changes in companies beyond the kind of programs that you're doing to deal with this problem? So someone mentioned agile project development, where you're dealing with, instead of giving a single number, you're giving a range. What kinds of developments, cultural developments, have you seen in the companies to move towards a better understanding of probability and risk?
Yes, so the agile development is just beautiful. It is really in the bullseye of solving these problems. If you can't deal properly with uncertainty, then just make your decisions more often as things change, right? You actually can prove using the flaw of averages that agile development gives you greater optionality, which is one of the things that the flaw of averages addresses. So that agile development is definitely helping to solve these problems with uncertainty. I think, interestingly though, when it comes to maturely dealing with uncertainty, you will find some industries like finance. So in finance, people look at risk return curves, and they have since the 1960s with regularity. In option theory, people are looking at uncertainty explicitly. But frankly, there's a huge amount of low-hanging fruit today to go out and adopt these methods today. And for example, when you look at how people do risk regulation, I think this is worth sharing. I think this is a very, very important. When people regulate risk, here's an important definition of risk. Likelihood of failure times consequence of failure. So the likelihood of failure, suppose the failure is, there's an accident, someone gets, and if it happens, there's one chance someone gets killed, right? Okay, but the likelihood, so LOF, suppose this is 10%. 10% chance. And the consequence is 1 fatality, right? And so this definition of risk says the risk here is that times that, or 0.1 fatalities. And by the way, this is used in regulation. All right, well, let me ask you this. What if there was a 0.01%, that's a 1% chance, oh, okay, let's see, of 100, of 10 fatalities? Well, wait a minute, that's still 0.1. What if there was a 0.01% chance, I got to add more decimals so we can even see it, chance of 100 fatalities or 1,000 fatalities? Oops, 1,000. There we go. It's still 0.1. So this measure of risk does not distinguish between killing one person and killing 1,000 people. And it is in common use in regulation. So there's a huge amount of low-hanging fruit for people to go out and learn about this stuff still in their organizations and change those organizations from within. But great question, and agile development is a step in the right direction.
That's fantastic. And so, and a big piece of it, of course, is having these Excel sheets, being able to play with the model in front of someone, to show, demonstrate that as the numbers change, how in real time that's changing the risk.
Risk intelligence now is being monitored, and some people have it and some don't. Gamblers have it because they've been involved in limbic analytics. They've got their butts on the line in the casino, and they're quite good at this.
That's excellent. Well, we're pretty much out of time. I guess I want to remind everyone that Professor Savage will be teaching this in more depth. I posted the link to the course in the chat box if you're interested. Professor Savage also has some edited videos on a lot of these topics on his website, so you can go there as well for tutorials and refresh yourself or to inform your company about these important topics. So I want to thank Professor Savage again today. I want to thank all of you for being here today, and we really appreciated your time, and we hope you enjoyed it. Thank you.
Thank you.